Okay, so we will be taking up a new topic, which is magnetic scalar potential and vector potential. Okay, so we had we have seen for electric field E, the relation with the potential, the scalar potential was minus del V, right? So what it was, what the scalar potential was, what kind of information it was giving was, so if I place a charge here plus, what we are seeing was that as you come closer to the charge, the potential increases. Okay, the value of this V was increasing. As you go away from the charge, the potential decreased. So this was why we had defined this, was like this was another way of calculating your electrostatic field. Given a potential, we know that our electric potential at a particular point, what will be the electric field at that point. So this we could have found out using minus del V. So the relation here was like as we go away from the charge, the V decreases. So same way we will come across this will define two terms, which is magnetic scalar potential and vector potential. In the electric field we are only looking at the scalar potential. So here we have the two potentials. So we have this identity with us, which is Maxwell's equation is the Maxwell's equation del cross H is equal to J. Okay. This is there with us. We also have another Maxwell's equation identity, which is del dot B is equal to 0. Okay, these are the two equations which we have with us. So in vector algebra we have this identities, which is like del gradient, curl of a gradient, del cross del V is equal to 0, which is where V is a scalar here. V is a some scalar. Okay, so we also have another identity which says that divergence of curl, divergence of some vector curl, some vector A is 0. We also have this identity with us. Okay, so now let's define a term which is called as magnetic scalar potential. Just like how we had this particular thing, just like how we had defined electric potential, let's define a magnetic scalar potential given by H, which is analogous to E, electric field intensity. This is magnetic field intensity, and this will be del Vm. So let's just say that we have this Vm, which is magnetic potential. So now if I substitute this here, I know that curl of a gradient is 0, right? If I use a vector identity, so I will get del cross del m Vm is equal to 0 will be true. So what it will also mean is del cross H is equal to 0, right? So this magnetic vector potential will exist when this particular quantity Vm will exist only when J, vector J equal to 0. Okay, otherwise it will not be existing. Just like del V, how we had for electrostatic field, this was Laplace's equation was satisfied by the electric potential for electrostatic field. We also have Laplace's equation for magnetic potential, which is del square Vm is equal to 0. So this particular Laplace's equation will be satisfied. This particular Laplace's equation will be satisfied by this magnetic potential. Okay, so one thing is we have defined Vm, and what we have also got is Vm, which is magnetic potential, scalar potential. It is defined only when